construction. So my object is algebroid, which was invented many years ago at the mid of the past century, and it appeared in many works and has a lot of different application in geometries, in the connection theory as means of treating the rank cohomology algebraic methods as invariant theory of foliation and pseudo groups of various types in symplectic and Poisson geometry and so on. As algebraic different also and as algebras of differential operators associated with some vector bundles, and this last points which be a main in my discussion. So let's proceed to the definition. Definition of the algebroid. Let M be a manifold. The algebroid or the manifold M or is the base M is a vector bundle E over M together with some bracket, Lie bracket on sections, Cartesian products of sections of E to this sections of E. And we have the module gamma E or global section, and also this manifold is endowed with some additional morphism, bundle morphism rho, eta, from E to tangent space to the manifold M, rho from E to Tm. And this morphism is called the anchor of our vector bundle. And all this together satisfies the following property, three properties. The first one, the bracket on the bundle gamma E is R-linear, skew-symmetric, and satisfies the Jacobi identity. So we have the standard Lie bracket. The second one, the action of this bracket on the vector 1 on F acts as the differentiation. So we have the following identity where rho x is the usual vector field defined on the manifold M, because rho x belongs to the tangent space of the manifold M, yes? And the third one, the morphism rho satisfies the standard homomorphism property of Lie algebras. So we have the commutator on the space of section gamma E passes to the commutator of the vector fields on the manifold M. So this object is defined in such a way, and here it was in some sense inspired by construction in differential geometrical structure related with symplectic structure on the manifold with endowed with the symplectic structure. So about the anchor. Anchor rho ties his brackets on gamma E to the vector field structure on M. And is this the last aspect was the main which was used for introducing this notion of algebroid. So in what follows below, I will deal with the canonical, the special structure of this algebroid, which was invented by Courant, and it is called and is defined on the product of tangent and cotangent manifolds spaces on the manifold M, and is defined by means of the following Courant bracket. So we have two elements, a pair of two elements. The first one will be considered as the section of the Tm. It will be vector field on the manifold, and in the second component alpha and B will be considered as a differential form from the Krasmal algebra lambda 1. So this bracket, it is very easy to check that it's really satisfy the Jacobi identity, and so we can. In addition, we can define on this vector bundle Tm multiplied by T's adjoint M, tangent and cotangent spaces, we can find that this construction in as a whole is metrized with respect to the following dual invariant parent. So this means that the following identity holds. This is standard adjoint at invariance of this bracket. So having defined the bracket, the current bracket above, we can proceed to the following definition. The manifold Tm, tangent space and cotangent space product of the tangent and cotangent manifold, they jointly with the bracket defined because the current bracket and the natural morphism projector mapping rho, which is projector from this manifold, from this product to the component, tangent components, tangent space components on the manifold M, is called the current algebroid. This current algebroid is one of the simplest version of the algebroid, Lie algebroid related with the manifold M and the structures, canonical structures on it, tangent space and cotangent space. So now we are going to analyze some special cases of our manifold for the case when the cotangent manifold, the cotangent space on the manifold M is endowed with its own Poisson structure, P. Poisson structure, you know, that is a mapping which maps differential form to vector fields, which and the structure on the image of this Poisson structure, which is considered to be non-degenerate, satisfies the standard Jacobi identity. So the inverse to the Poisson structure mapping is in the differential geometry is called the symplectic structure. So then using this Poisson structure, one can construct two vector fields A and B, where A and B corresponding to differential form alpha and B, and to construct the next bracket on the cotangent space, or the cotangent space T star M. So we see this bracket is exactly the part of the bracket defined from above, or so you see, but reduced on the first component, on the second component of our current bracket. So we see that this reduced current bracket becomes in its second term identity reduced to the bracket on the cotangent space. So you see, and one can also check, easily check that this bracket on the cotangent space also satisfies the Jacobi identity. So we have Lie structure on the cotangent space, which is in some sense obtained from the Poissonian structure on the manifold M. So we also have the following mapping, morphism structure for this case of algebroid, which we obtain, and the anchor P, which is a main component of the algebroid, consigned exactly with the Poissonian structure. You see, because it satisfies the following homomorphism property. The P alpha B exactly is the commutator of the vector fields P alpha B, PB for any differential form alpha and B. So we have this reduced current algebroid on the cotangent space with this reduced bracket and the anchor P. What is interesting that this bracket, which was defined above, so you see, I forgot to say that LP alpha denotes here the standard Lie bracket of the vector field P alpha is of the beta form with respect to a vector field P alpha. So the standard, the usual Lie derivative of the differential form. So if we consider this differential, this bracket, we can rewrite it in the following equivalent form. So we see we have the left-hand side is our bracket, and the right-hand side coincide with the coadjoint action of the vector fields P alpha and PB taken with alternate sign, because we have this action, coadjoint action of alpha. Here we have alternate coadjoint action of P alpha on B, and the following the component, the exact form component, which left from this definition of the bracket on the cotangent space. What is important, this in the case when P mapping, Poisson mapping as an anchor, it can be generalized to the following form. So we can consider some tensor element R belonging to the tensor product of tangent space Tm on itself, and which to which there corresponds some linear mapping from the coadjoint cotangent space to tangent space, because it is kernel of this mapping. It can be considered, this tensor element can be considered as a kernel of this mapping, and we can rewrite the whole right-hand side in general form as coadjoint action of two mappings, R beta and R alpha, where R is some tensor element which should be taken in such a form that the alpha, the commutator on the cotangent space will coincide exactly with this alternated coadjoint action of this tensor, this linear tensor mapping on the differential form. So we have the following representation. So the problem is that we need to impose some constraints on this tensor element, under which this mapping R from the commutator structure on the cotangent space to the Lie algebra structure on the tangent space of vector fields will be more homomorphic. So we should impose some additional constraints on which, owing to which this mapping will be homomorphic of two Lie algebras on the tangents, cotangent space and tangent space. The following proposition solves this problem as a special case. Let an invertible tensor element R allows the direct sum splitting in the following form: K plus eta, where k belongs to the symmetric part of this tensor. It's non-diagonal symmetric part, and eta belonging to its skew-symmetric part. In this case, we can define the following related mapping: D equals k composed with the inverse eta of the mapping eta from tangent space to tangent space. So, and if this composition of two mapping k and inverse to eta is a derivation of the vector field algebra on the manifold M, then, so we have the standard condition on the commutator, then for any alpha and b, should be, if this condition is satisfied, then the mapping D will coincide exactly with the generalized anchor of the algebroid, Lie algebroid constructed above with owing to, based on the tensor element R. So this condition is, if this condition is satisfied, then the following corollary holds. Let a tensor R satisfy the condition above. Then the triple is a generalized current type algebroid with a related anchor morphism R. Corollary, the second corollary, the following deformed commutator structure LABD equals to this to the expression 11 determines for any A and vector fields N and B the second Lie structure on the tangent space. Is satisfying the naturally the Jacobi identity. What does it mean? This means that we obtained the algebraic structure owing to which we can define on the tangent space Tm to the manifold M two Lie structures. The first one is a canonical Lie structure on the manifold of vector fields, and the second is deformed Lie structure owing to the existence of this derivation D. Okay, so if we have the structure, the algebraic structure similar to the above, in the case when the tensor R satisfies the property allowed, we can proceed to some example of the picture just described. So the example is based on the following construction. Let's take some manifold M, which will be considered to the to the so-called product of diffeomorphism group of torus Tn and dimensional torus Tn, depending on some parameter lambda parameter. So some words about this construction. So we consider this loop diffeomorphism group, which is constructed the following way. We take this circle in the complex plane, and we consider all diffeomorphisms of this circle, mapping of this circle into diffeomorphisms of this diffeomorphism group. So then we can holomorphically extend this mapping from the circle S1 inside of this disk D plus of this circle and outside of this circle with respect to the parameter lambda belonging to this complex plane. So this way we will obtain two parts of diffeomorphic group of this torus, analytically dependent on the parameter lambda, inside and outside. And the normalization of this diffeomorphic group is taken in such a way that any element of G belonging to the diffeomorphic holomorphic diffeomorphic group outside the disk at infinity, lambda tending to infinity, complex parameter lambda is equal to 1, to the unit mapping of our group. So this object allows to construct the Lie algebroid of the current type. If we take the tangent space to this diffeomorphic group, and respectively cotangent space. So we have Lie algebra of vector fields analytically depending on parameter lambda inside and outside of the unit disk on the complex space, complex plane, and we have our Lie algebra of vector fields, which contains which can be split into two parts, and the splitting will be direct. So we have two parts, diffeomorphism plus minus, analytical inside and outside, and we need to construct the anchor of our algebroid. And this anchor can be constructed the following way: when we if to split our tensor R, the wave on the R depends analytical dependence on the complex parameter. So we have the direct splitting of our anchor into two parts, symmetric and antisymmetric, and we can construct the following object: P plus minus equals to 1 plus minus D minus, where D was defined before. So if we construct these two operators, two linear mapping from Lie algebra vector Lie algebra vector fields on the torus to the to itself, to its component, we can check that these two parts are projectors on the exactly on the part diffeomorphism vector fields analytical inside and on the component analytical outside of the disk on the complex plane. So this property, projector property, is very important because the following theorem can be checked or proved that cotangent space, so the basic space of the Lie algebroid with which we were discussing before, is exactly Poissonian with respect to the following deformed Poisson structure. So we see that if we take this Poisson's bracket on the cotangent space, so we can check that this bracket can be identified with the mapping of this element L on the commutator of vectors fields on our torus with respect to deformed Lie bracket. So owing to this fact, so we have Poisson structure. So we arrived to exactly to the reduced current Lie algebroid, and as a corollary, we can formulate the following property that let E will be a set, the set of smooth functional on this cotangent space to our vector fields on the torus, which satisfies the following properties. The coadjoint action of this gradient of this smooth functionals equals exactly to 0. This way we construct the set of all possible smooth Casimir functional on the cotangent space to the Lie algebra, analytical Lie algebra on the torus, which are invariant with respect to the canonical coadjoint action of the loop diffeomorphic group defined before. This term loop means that we consider this group as mapping from the C1, from the circle C1 to the diffeomorphic group, and this way we construct the loop diffeomorphic group, analytically continued inside and outside of the disk. So then, if we have the set, how constructed owing to this definition, the Casimir functional on this cotangent space. So the countable, any countable sequence of independent, functionally independent element gamma yod from this Casimir sets appear to be commuting to each other with respect to exactly the deformed Lie Poisson structure D just defined before. So you see, we have this Lie Poisson structure, and we can prove that all these functional are commuting to each other, and generate an infinite hierarchy of completely integrable Hamiltonian structure. So I should mention here that all the set of Casimir functional on the cotangent space to the diffeomorphic group on the torus are defined owing to the standard Lie bracket on the tangent space. So we have the standard Lie bracket of vector fields on the torus, and so Casimir functions are related with this canonical Lie bracket on the tangent space to the diffeomorphic group. Yet we have constructed the deformed Lie bracket, Lie Poisson structure, with respect to which, in general, Casimir function should not commute to each other. Yet, in this case, the theorem states that really all these functions are commuting to each other, and taking into account that our bracket is deformed, and all invariants are commuting to each other, we can state that the corresponding coadjoint action of the deformed function vector fields generated by this Casimir function generate non-trivial vector fields on the cotangent space to the diffeomorphic group of the torus, and owing to the fact that this Casimir functional are commuting to each other, we this way constructed an infinite hierarchy of completely integrable flows of Hamiltonian system on the cotangent space in the following reduced form, and as a corollary, all these Hamiltonian systems owing to the commuting of the functional, these all flows are commuting to each other also. So we arrived at the set of Hamiltonian system, which are invariant with respect to the abelian group of symmetry. In the case when this abelian group of symmetry is complete, is of maximal rank, coinciding with the half of the dimension of the manifold, our manifold, cotangent, no, our manifold diffeomorphism group of the torus. In this case, we can state that our Hamiltonian system are really completely integrable. So this way one can construct an infinite hierarchy of new Hamiltonian systems on the diffeomorphism group of torus, which really are of very interesting form, and in many cases coincide with very interesting flows on some functional manifolds, and describes in some part some geometrical structure, so-called quasi-conformal metrics on
Professor Prykarpatski,
Einstein
sorry.
manifolds. Sorry?
I'm sorry to interrupt you. Yeah, sorry, go. Just it's time right now. So your time
Yes, I just finished. So we have some references, and thank you very much for the attention and introduction to the new object in the algebra and geometry, algebroids.